friends, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. So I am currently in the process of rearranging my recording setup, so it's a little janky right now, so you'll have to forgive me if things sound kind of a little bit off, but you'll have to let me know how things go with this, because this definitely is an experiment. But speaking of which, if you have been listening to the show for a while and you have any questions that you want answered on the podcast, you can shoot me an email at contact@darkassassinsinc.com. The link for that is in the show notes below, as always, along with all of the other various links that'll be included in this week's episode, since boy oh boy do we got a doozy on our hands, and this is potentially the one instance of getting a perfect score where you quite honestly wanted to get the exact opposite, because within the past week there has been a massive vulnerability discovered in Linux, specifically the XZ Utils package, which is on systemd systems linked with SSH, and long story short, if this backdoored version of XZ Utils is installed, some attacker somewhere in the world has a backdoor with root access to your system. So we're going to be getting into that this episode, but before we do, let's start off with our trivia question. So kind of in the same cybersecurity realm, the Onion router, or Tor, was invented in the 1990s. Who invented it? So who invented Tor? And that is your trivia question for the week. So seeing that this episode is pretty much all cybersecurity all the time, we're going to skip our cybersecurity tip, because we are going to potentially talk about some potential mitigation strategies to this backdoor during the explanation. So we're going to do that later in the episode. So now it's time for what nerdy stuff have I been up to this week? So I was kind of all over the place this week. So one of the biggest, so I guess to touch on last week's episode, the vector implementation that I'm working on in C, I'm pretty sure code-wise that's done. At this point, I'm just updating some things like the README, making sure there's make files, and the make files work for various compilers on various platforms, all that good stuff. And I bet you can't guess which make file gave me the most trouble. And if you guessed Windows, you would be correct. Specifically, the native Windows compiler, I guess I'm calling it, or MSVC, the Microsoft Visual C compiler. It comes with Visual Studio. It's when you type CL. The make file it uses nmake, which is similar to the GNU make file format, but it also has its differences, and someone that's used to writing GNU make files, it's kind of annoying because not everything works the same way. And I mean, the compiler flags being different, I mean, that I guess just kind of comes with the territory. It's something you'd expect, but some of the syntactic differences, I wasn't a fan. Needless to say, I sunk many hours into trying to get this working, and eventually ended up just settling on only creating a static library rather than a dynamically linked library, or DLL, because for whatever reason I could create the DLL, but then I was never able to link against it, and every chance I did just gave me absolutely nothing in the exports. Like, definitions to be able to be created to a temporary .lib that you then link against, which then links to the DLL. And yeah, it was just a mess. I think probably what the issue was you have to, I'm assuming based on some of the looking I was doing online, it seems like you have to like explicitly export the functions that you want to have, visible from the dynamic link library, like specifically marked within the source code itself. That's kind of the interpretation I was getting. I don't know, maybe I was wrong about that. I've never really created a Windows DLL before with the MSVC compiler. I've done it with the GNU compiler since I wrote that function logger library a few months ago. And even ironically, this vector library, I'm able to create a DLL for it on Windows. It just only works with the GNU suite of tools rather than the Microsoft ones. So yeah, kind of interesting there. But that was what I was up to on that front. So just a few loose ends here to touch up, and then I will get that pushed to the old GitHub. And speaking of pushing to the old GitHub, I have another update that I'm going to be pushing there too, which is for my command prompt bypass script, which is another Windows tool that I guess it's a tool that I created, which as a quick recap, the point of this batch script is to allow you to have a Windows command prompt even if your administrator has disabled the command prompt through the Windows settings. And if you ever look up how to re-enable the Windows command prompt, it always requires you to have admin privileges in order to do so. But the point of this script was basically to give you a command prompt without needing any admin access whatsoever. And I have a whole blog post about it, so you can go look that up. If you go to my GitHub, it's linked there as well. But the gist of it is it's a batch script, which is kind of the command prompt scripting language. And it basically is an infinite loop that nests taking in your user input and then piping that into another batch script, which basically does all the executing, so you can have all your environment variables and all that there. So you basically get all the features of the command prompt essentially running through one-time uses of calling CMD, which is the command prompt, and piping all that to the command prompt all from one script. So basically giving you full access to the command prompt without actually having access to the command prompt. So this was a cool script that I kind of liked making, and I made some improvements to it because when I kind of switched over to having, well, even from the beginning, but specifically when I switched to doing this new variant of putting everything into a separate batch script, and then that batch script being run, and through the course of that running it, make sure it includes all the environment variables and then runs whatever you want to run and basically allowing it to work. But in order to do that, I was making some like temporary files and putting all this in a temporary directory, and then when you would exit the script, assuming you actually typed exit, the directory would essentially clean itself up and delete itself. The issue with that was if you had multiple instances of the script running, they would be overwriting each other's temporary files, and that could lead to some rather interesting circumstances. And in other cases, it would just have issues finding them at all, and that could also cause issues. So basically, this new variant, first what the script does is it gets its PID, or its processor ID. So if you're not familiar with what processor IDs are, whenever you start a new script, a new application, whatever, you essentially get an ID from the kernel that basically, tells your process what you are, so it scheduling things and whatnot. So the thing that's nice about this is it's unique. So what this allows you to do is you can create temporary directories or temporary files and basically append this ID to it, and it'll basically be unique. So what I did was I appended the processor ID, and this will come important later as well. So I append the processor ID to the temporary directory to basically ensure only that process is going to be modifying the files within that folder. So this gives you the added benefit of when you launch another process or another instance of this script, it doesn't overwrite your other terminal. So you can basically have multiple instances going at the same time without overwriting each other. Awesome. Problem is, when you try to delete, if you don't type exit, the folder doesn't get deleted. So the problem is, because they're not all using the same folder, this could basically create a buildup of all these temporary directories and not be good. But that's where the benefit of adding the processor ID to the folder name comes into play, because what this allows me to do is when you launch a new script, when you run the script whenever you run it, what it does first is it checks every single one of those temporary directories. It basically checks, well, first it checks if there are any at all. And if there are, it strips the PID off of that folder name and checks to see if that process is still running. If it is, then it doesn't do anything. But if that process isn't still running, that implies that that terminal window, that command prompt window, has been terminated, but it wasn't terminated with exit, and the temporary directory still exists. So when you launch the new script, what'll happen is it'll check all that, and if it finds that there is a temporary directory that no longer has a process associated with it, it'll clean all that up for you, basically removing all that clutter and ensuring that your home folder doesn't get cluttered up with all these temporary directories. So I'm pretty hyped about that update. So that's of course on the old GitHub, so you can go check that out. And then as far as the video game updates, not really much there. As you can see, I was working on other things. But I did do a little bit, mainly just some basic refactoring stuff. Nothing too serious, no new real big feature updates or anything like that. But with that, I think it's probably about time we get into the main course of this episode, which is the backdoor in the XZ Utils. So this is basically the definition of a supply chain attack. So essentially, there's a kind of a lot to this, and we're going to kind of go through it in bits and pieces. But kind of as a quick summary, the code, so I guess let me back up and give an overview. So all the information I'm going to be talking about in this episode, I did not find it. I was not one of the security researchers digging into this. I am just a code monkey who occasionally breaks stuff in his home lab, who happens to have a background in cybersecurity. This stuff interests me, so I did some digging on the folks that did the digging to kind of figure out what was going on, and here you go. So as a bit of an overview, the XZ Utils, or the XZ library, also known as libLZMA, is a library that's used to implement the LZMA compression algorithm. And this specific exploit and backdoor scores a perfect 10 out of 10 for its CVSS score for its CVE, which, in case you didn't know, you don't want a 10. 10 is the worst, most severe, most critical vulnerability, so it's definitely something you do not want. And the reason why this scores so highly is because it's more or less directly linked to SSH, which is the secure shell. So basically how everyone remotely accesses their Linux servers. And if you didn't know, pretty much the entire world's servers run on Linux. So this is potentially a massive, massive issue, as we will see. So the reason why this is an issue, because it's not only that this compression library has this backdoor, because that in and of itself doesn't really mean a whole lot, because as we'll see, the backdoor literally has nothing to do with the the normal functionality of the compression library itself. It really only becomes dangerous when it's linked with SSH that's running under systemd. So essentially what this means is, even if you have a system that has one of these infected versions of the library, if you're a system like Arch or Gentoo that technically has this backdoored version of the library but don't use systemd, your SSH version isn't affected by the backdoor, so you essentially have nothing to worry about. But even with that said, though, it's generally speaking best practice to not have packages or libraries installed on your system with known backdoors. I mean, at least as far as we can tell, this backdoor is not exploitable on systems that don't have systemd running SSH. At least as of the recording, there is no way to exploit this backdoor unless it is through SSH running under systemd. So the specific library in question, the version numbers, are liblzma 5.6.0 and 5.6.1. So if you have one of those versions and your Linux distro uses systemd, then you are vulnerable. If you have one of those versions and your Linux distro does not use systemd, you are not vulnerable, at least by the known exploits of this backdoor. And we'll get into in a little bit here how you can determine if your system is actually vulnerable. But generally speaking, if you're running an LTS, Enterprise, or stable Debian distro, you're almost certainly fine. It's only if you're on one of the bleeding edge distros like Fedora or Debian testing or a rolling release that you would potentially be vulnerable to this. So getting into how you can determine if your SSH is vulnerable, what you can do is you can log in to your Linux system and you can type LDD space /USR or user /sbin/SSHD. And if you don't see liblzma at all, that means your system doesn't use systemd and you're fine. If you do see libzma there, you'll probably see something like liblzma.so.5 and then equals caret and then /lib/ ... whatever the path is, liblzma.so.5. And then what you can do is if you take that path, so that /lib/ whatever /liblzma.so.5 whatever, if you take that path and you do an ls-l followed by that path, you'll get the full version of what the library is that's running. And as long as that version is not 5.6.0 or 5.6.1, you're fine and you have nothing to worry about because that version isn't installed and therefore the backdoor is not installed on your system. So that's kind of a brief overview and how you can know if you are affected or not. So now let's kind of get into how this works, kind of how it was discovered, the timeline, because this was a very long, drawn-out process. It wasn't just one day it just appeared or got committed into the source code. It's a lot more nuanced and a lot different than that. So the backdoor was created in such a way where it wasn't even included in the XZ source code at all. And that might seem confusing because it kind of is. But the exploit, the backdoor itself, was also obfuscated to the T, which we'll get into in a little bit. And the way that they were able to hide this backdoor was they hid it inside a compressed XZ file in the test directory. So kind of the irony here is the backdoor for XZ was hidden in an XZ file. So little ironic there. But the reason why this went unnoticed was because according to the repository's own README file, which granted was in place, and this verbiage was in place before this backdoor was even put into the test directory. But according to the repository's README file, the test directory is, quote, a directory that contains a bunch of files to test handling the .xz and .lz files in decoder implementations. Many of the files have been created by hand with the hex editor, thus there is no better source code than the files themselves. End quote. So this kind of makes sense, right? You're going to upload test files that are the file that you're trying to test the implementation of in order to verify that your code actually works and does what it's supposed to do. So, and of course, if you're just uploading a test archive like that, like it even says, are usually hand created with a text editor, it's probably not going to generate much scrutiny if you upload a new test file, be like, this is to test, some new implementation that we're working on in the source code, right? And of course, because the exploit and the backdoor is not in the source code, it becomes that much harder to actually verify and scrutinize these files, because the code itself isn't, plainly visible that anyone could go see. And this is kind of a key aspect where these kind of supply chain based attacks happen, is because you have this attack surface like this that people aren't really looking as closely at like they would, say, if you were actually, writing changes to the source code itself. So the reason why this is so dangerous in combination with SSH, kind of as we've kind of alluded to, is when SSH is running as a daemon through systemd, it first off, it links to liblzma, which it doesn't if it's not running with systemd, because OpenSSH doesn't technically need to link against liblzma. It just happens to if it's running with systemd. But the reason why this is so dangerous is because when it's running as a service like this, it's running with root privileges. So when you're running SSH as a service like this, it's running with root privileges in order to properly privilege the authenticated user that's coming in. So when you log in to an SSH session, the server has to check your user and ensure that you have the proper privileges in order to be able to do what you're allowed to do. And the only way you can do that is if you are root, in order to assign whatever privileges that are necessary. So essentially, if you can exploit this, you're essentially exploiting a application that's running as root. And if you've listened to the podcast long enough when we've talked about these kind of exploits, if you exploit a process as root, you then gain root access to the system. And if you're not familiar with what that means, that essentially means you can do whatever you want and the operating system won't tell you no. So if you're a threat actor, that's obviously the best because you can do whatever the heck you want and get away with it. If you're a systems administrator, that's an absolute nightmare because someone can completely mess up your system. So yeah, getting root access on a remote system and being able to execute code or run arbitrary commands is the definition of a worst case scenario, and that's exactly what this backdoor allows to happen. Now, it should be noted that there is only one, I would say person, but based on the research that security researchers have done, it's more likely an entity, as we'll discuss in a little bit. But only a singular entity would actually be able to exploit this backdoor, because the way it was implemented was the public key of said person, individual, group, whatever. Their public key was embedded and obfuscated within this backdoor itself, so only them with their private key would be able to access any Linux system, of course, that was running OpenSSH with systemd, and would have root access. Now, again, it should be noted that only the person with the private key would actually be able to perform this exploit. It's not like Joe Schmo or some script kiddie would be able to run this exploit unless they somehow got a copy of the private key, which, who knows, maybe whoever created the exploit would sell the private key on the dark web so anyone could gain access to it. Who's to say? But the point is, only the person that would have the private key would be able to perform this exploit. Now, I kind of touched on the fact that it was kind of not likely to be an individual, and the reason why that is the sophistication of this attack, the level of obfuscation, and the length at which the attack took place, since this was literally years in the making. It wasn't like some random person pushed a code change like 2 weeks ago, and that was the backdoor. This exploit, if you will, has been years in the making, and the OPSEC, or Operation Security, by this individual, quote unquote, or entity or whoever that committed the backdoor into the repo, leads security researchers to suspect that this wasn't a singular individual, but rather a state-sponsored operation. So as Brian Curbs from Curbs on Security points out, the email address that was used for the past couple years by the individual who committed the changes has zero trace outside of GitHub or GitLab and a couple of various mailing lists that were related to the XZ Utils development. He also notes that in cases like this, where an email is a single-use or a single-purpose email, it's usually created for fraudulent reasons or because someone is paranoid about privacy. But the reason why he concludes that this wasn't an individual but rather a state or a group was because there was no slip-ups, and it's very hard if you're a single person to not have a single slip-up over multiple years when you're just, a single person. The likelihood that you're going to accidentally slip up, use that email for something else, or accidentally say your real name or something like that is generally fairly high. So that's why him and other security researchers have concluded that this was actually a state-sponsored effort. And I guess I will leave you, the listener, to imagine what potential state that was that did the sponsoring. But according to the security researchers, it wasn't just specifically an individual. So I guess the next question is, how did we figure out that this exploit happened? Like, how did we even figure out about this vulnerability in backdoor? So there was a guy over at Microsoft named Andres. I'm not even going to try to pronounce his last name. But there's a guy named Andres. I'll link the thread below. And according to him, he accidentally discovered the vulnerability when benchmarking Postgres changes. So the irony here is he didn't even try to find the backdoor. He just happened to stumble across it by accident. So he happened to be, I guess, running Debian testing. And according to him, he was doing some micro benchmarking, and he noticed some slight system, I guess, latency lag slowdowns when specifically tied to the SSHD process. And he was surprised by the amount of CPU usage that was going on, which then proceeded to him to start investigating and profiling SSHD, which showed a lot of CPU time for liblzma. And then he did some additional digging and was able to discover what was going on here. So one thing he points to is valgrind errors. So we'll touch on that a little bit later when we go through the timeline. But now, do you guys remember when I was obsessing over fixing all the various valgrind errors in my programs? Because that was a thing. And the reason why valgrind errors they're not necessarily a red flag, but because sometimes they can honestly just be very inconspicuous on the surface, but they also could be signs of possible vulnerabilities hiding in your code just waiting to be exploited. Like in this case, there were valgrind errors that popped up, and, they can definitely be a signal that there could be potentially exploitable vulnerabilities in your code. But it also goes without saying that just because your code doesn't have any valgrind errors doesn't mean it's free from vulnerabilities. I think that's fairly obvious, but just got to make sure because, there are many things that can play into vulnerabilities. For instance, there's a chance that when you ran it through valgrind, you missed the edge case that would cause the valgrind error. There are potentially other logic errors that could cause potential exploits in your code. There is definitely multiple ways that vulnerabilities can end up in your code, but seeing valgrind errors is definitely something that you should fix before you push anything to production. But as I alluded, that's not where the story starts, and it actually goes back quite a ways, kind of as I alluded to before. So to start things off, I have a link, the timeline I'm going through here, I have linked in the show notes below if you want to also go through it. But between 2005 and 2008, that was kind of when the design for the XZ file format was kind of created, and when it kind of started, the XZ Utils kind of started being incorporated into the Linux kernel. And come 2021 was when the attacker that was the one that signed and pushed the code with the exploit first comes onto the scene. So keep in mind, this is 2021, like close to the end of 2021, but still 2021. It is now 2024. So this has been quite a long time in the making. So the person, Gia Tan, I guess is their name, they first push a patch back in October of 2021. And then throughout the course of 2021 and 2022, they continue to, make updates to XZ Utils and just kind of showing themselves to be a quality developer. And then as it proceeds, the actual maintainer kind of, is really starting to admire this new kid on the block, I guess you will, for all the great work he's been doing for the project. And eventually he kind of toys with the idea of making a maintainer, and then he eventually does make this guy a maintainer, and then continues to, update builds and do build releases, and, continues to write patches and add things. And then here, I guess, is where some funkiness kind of starts to begin. So the attacker that was the one that pushed the backdoor disables the ifunct support during OFA's builds back in July of 2023. And then the attack kind of starts in this year, 2024, back in the end of February. So back in the end of February was when the hidden backdoor binary code was pushed into the test directory back in the end of February. And then the builds for 5.6.0, the tag for that build was created the next day on February 24th. And, that was where the malicious code was included within that version of the shared object library. And then it's basically the same day, Gen 2 starts to see crashes with that library, but it didn't seem to be anything necessarily specific with the hidden backdoor, but just, I guess, other things in general, other changes to iFunk changes that were made. But again, Gen 2 doesn't use systemd, so it doesn't actually have the backdoor included in it. And then Debian adds the XZ Utils 5.6.0 to its unstable branch. And then the attacker that pushed the backdoor is kind of emailing others, asking them to, see if they can include the new version in their builds. And then let's see here. Landlock detection configuring scripts updated some part of the build script. And then later on, here is kind of where the Valgrind errors come up. So in March 4th, Red Hat distribution starts seeing Valgrind errors on libzma's get CPU ID entry, which is the entry point for the backdoor. And this is kind of where the issues should arise, right? Like, you're starting to see Valgrind errors. That's kind of out of the ordinary. And then allegedly the guy fixes a couple more bugs, and then pushes, those changes. He supposedly updated some Valgrind fixes, but, yeah. We'll see about that. And then he committed new versions of the backdoor update files, which added even more obfuscation to the object files themselves. Tags that new build as 5.6.1, and then pushes that to have it, be included in future versions of the various Linux distros. And then Debian updates to this new version in the Debian unstable branch updates to 5.6.1, and this attacker tries to get Ubuntu, or he files an Ubuntu bug to get XZ Utils updated to the new version, the 5.6.1 from Debian. Ubuntu didn't actually end up doing that, and then we get to the attack being detected. So that's where Andres discovers the bug initially and reports it with the CVE of 2024-3094 on March 28th. And then also on March 28th, Debian rolls back from 5.6.1 back to 5.4.5. And then Arch Linux changes the 5.6.1 to build directly from Git rather than the prepackaged version of the binary, essentially to basically not include the backdoor. And then just, more announcements of the backdoor being discovered and basically letting people know. So that's kind of the timeline up to today, kind of a quick run through. Again, like I mentioned, I'll have the full timeline linked down in the show notes below if you want to go through it yourself. Now, we kind of touched on bits and pieces of how the exploit in the backdoor works, but I want to kind of capture all of those bits and pieces into one place and really go through how this exploit works. Now, again, I wasn't the one that discovered how this works. I'm just going off of what other cybersecurity researchers have found and information that has been made publicly available about how this works. And again, I will have links in the show notes down below if you are interested in looking at any of this stuff further. So, So first off, the code that performs this exploit, the backdoor itself, is not in Git and it's not in the source control of the repo. What it is in it's in version controlled obfuscated makefiles and compressed quote unquote test binary archives to test LZMA. So basically, some malicious obfuscated makefiles were pushed and some bogus binary archives to test, quote unquote, test LZMA were also pushed. And inside those test binary archives is what contains the malicious code. So what ends up happening is the malicious binary archives get uncompressed and then hook directly into the build process itself through those obfuscated bogus makefiles. So during this injection, there's a precompiled binary object that's included inside one of these test binary archives that was pushed. So one of the malicious archives that got pushed contained a malicious binary file, which then gets linked into the project itself. And that is where the backdoor is installed. So the backdoor gets installed directly into the library without actually being in the source code at all, because through this, this obfuscated bogus makefile, it links this binary from its test archive and links it directly into the library during the build process. So the most recent version, the LZMA, the 5.6.1, that binary object even further obfuscated and removed symbol names from the object itself. But how it actually gets linked in and causes the backdoor is during the linking process, the backdoor changes the value of RSA public decrypt to point to its own code. And in its own code is where the author's public key is stored, and that's also, how it's able to... So essentially what that means with their public key being stored in there, that's how when the threat actor connects with their private key, their version of RSA public decrypt runs, and because their public key is in there, it can basically check to see if it's, the threat actor that's trying to connect and basically authenticate them and allow them in. So a quick overview of the linking process, if you're not familiar with how the linker works. Basically what the linker does is it maps where functions are located, so into the actual executable itself. So when you compile your program, or you compile the individual files that make up your program, if that's kind of the point of what include files are. So if you have an include file, you say, hey, compiler, this function isn't in this file, but don't worry, I'm including the file that has that function. So for instance, if you have 3 files, one that's utils.h, one that's utils.c, and then you have your main.c, if inside your main.c you have a function that's called something like check value, basically when you compile the code initially, the compiler will see check value, doesn't see it in the main.c file itself, but sees you included utils.h, which has that function defined, so it can continue through the compiling process. And then the linker process is what comes through at the end and basically says, okay, in main.c here, they're calling check value. Now I need to go find where check value actually is and then essentially link that portion of the code to there. So when you get to that point of the execution, you can actually jump to the right place and execute the code as you intended it to. So essentially what was going on here is the backdoor hooks into this linker process, and rather when the linker returns the address location for this RSA public decrypt, it essentially catches that, intercepts it, and rather than giving that address back to the linker, it gives the address to its own code back to the linker. So then whenever you try to run the RSA public decrypt, the code from the backdoor gets executed rather than the actual RSA public decrypt code. So that's kind of the deep dive into how this actually got put into the library itself and how it fits in with SSH and how it can be exploited. Now, actually seeing this exploit in action, I have a link down in the show notes demoing it. But essentially in practice, when all this is built and you connect to the SSH server, or when you basically, well, first off, when you connect to any SSH server, you do a certificate exchange with the server as part of the authentication process. And this is where the backdoor actually exists. So what the backdoor does is it checks to see if the certificate has been signed by the attacker. And the way that this is done is essentially the attacker, well, just the general certificate process in general, how that works is, first off, you sign the certificate. So you take the certificate and then you sign it with your private key. And how signing works is you essentially take the hash of whatever you're trying to, get the signature of. So in this case, it's a certificate, but you could also do this for text files, PowerPoint presentations, binary objects. You could do it for anything. So basically what you do to get a signature is you take the hash value of that file and then you encrypt it with your private key. And the way that you verify that signature is you yourself take the hash of the file in question, and then you decrypt the signature with the public key. And if your hashes match, the hash from the decrypted value and the hash you generated, if those match, then you know that that signature was generated by that private key. So essentially what's going on here is the backdoor does this check. So it checks the the signature coming through, and checks to see if it is coming from its private key. And if it is, then it goes to the next phase because, first off, it can take advantage of this because, as we mentioned, inside the backdoor itself, the private or the public key is embedded inside the backdoor. So during this, the backdoor also, rather than doing the full certificate thing that normally goes on, the backdoor has been implemented to basically embed the payload that you want to exploit within this cryptographic key exchange process. So it's basically impossible to detect this over the wire or over the internet, or if you're doing any kind of packet capturing, because all this stuff is just encrypted anyway. So you're basically not going to be able to see that someone is, sending arbitrary code or arbitrary commands to be run on your SSH server. All you're going to see is just encrypted, garbled nonsense. So making it even harder to actually detect what's going on here. And to add even further complexity to this, inside the payload itself is an encrypted blob, and this blob is decrypted by a symmetric key, which is also embedded within the backdoor. And then inside that decrypted blob, amongst other things, is what actually contains the command that you wish to execute. And again, because this is running as a system service, it's running as root. When you run this command, it's being executed as root. Meaning whatever you type for that command will be executed without question. So yeah, definitely not a lot of good stuff going on there. And again, if you want an actual visual representation of how this exploit works, I have a video linked down in the description below in the show notes. So yeah, kind of a wild world in the open source community this past week. I guess the good news is, if the bright side is, in all honesty, this got caught fairly quickly, because if we look back at the timeline, the attack was detected at the end of March, and it was the first instance of the exploit being injected was around the end of February. So it was only potentially out in the wild for about a month or so. And because especially the enterprise world moves very slowly, most of the enterprise distributions don't even have the backdoored version of the library even included at all. Even if they use System D, the backdoor version that would make you vulnerable isn't even included. It's only really included on the bleeding edge distros, which generally speaking are on developer machines or personal machines. They're not really running on the servers that run the internet, right? So that is potentially some good news. And the other, I guess, some other good news is some of the other bleeding edge distros like Gentoo and Arch Linux, for instance, don't actually use System D. So even though they had these vulnerable versions of the XZ Utils on them, they weren't actually exploitable, at least as far as we can tell, because their version of SSH doesn't use System D and therefore doesn't link to liblzma. So that is some additional good news. And since this has all come out, kind of like I said, some of the distros are changing their build process to essentially ensure that this backdoor isn't included, or even just rolling back to older versions of the XZ Utils to ensure that the version hasn't been included. So this is still definitely a developing story. There's still changes that are going to happen, but this has been kind of a big wake-up moment for the open source community, because if it wasn't for our boy Andres, the savior of Linux servers around the world, who knows how long this vulnerability could have been gone unnoticed. And that's basically kind of what the definition of a 0-day vulnerability is, right? Something that goes unnoticed and is there able to be exploited and nobody knows it exists. And this happens in proprietary software, it happens in open source software. And the reason why this vulnerability in particular was so, kind of such a wake-up call was because it wasn't in source control, at least not in the, normal sense. It wasn't like the maintainer or one of the developers wrote in the source control for XZ Utils, like in the plain C code that you can read, the exploit in the backdoor itself. It was included in a test archive that was because of how the test archive was compressed and whatnot. It's not like you can run something like strings on it and view all the strings that are inside it and kind of see what's going on in there, plus all the obfuscation that went on with the precompiled binary object. I mean, it's just a mess. So now I guess this kind of lends credence to why open source is good in kind of a weird twist, because while yes, this happened to an open source project, at the same time, once this got notified, basically everyone and their grandma was jumping on this. Obviously not everyone and their grandma, but the entire cybersecurity research community and everyone was getting in on this, trying to reverse engineer this exploit and backdoor, figure out how it works, and really try to understand what is going on here, how this happened, and that kind of a thing. So, and I guess you can't really necessarily blame the maintainer of the repo, because it was essentially just one guy, and expecting them to be able to, verify every little thing, especially that was, kind of, as I mentioned, closer to the beginning of the episode, why this was such a, large attack surface, uploading a test zip, essentially compressed archive to a test directory as testing data. I mean, what, especially when this is coming from a trusted developer, right? Like the guy that uploaded the backdoor, at the point he uploaded that archive, had been committing and providing quality changes for like over 2 years. Like, he had been a quality kind of cornerstone developer for this project. So if you see someone that's like, your main go-to developer, and they upload some changes to like the testing directory, are you going to think twice? I mean, I'd kind of doubt it. So, I mean, it's kind of hard to blame the guy, that the main maintainer. And I mean, I guess you could say that like any change that gets put in, you test it thoroughly yourself before you'd accept like the pull request or whatnot. But in all honesty, you probably wouldn't even notice, right? Like, the guy that discovered the vulnerability, Andres, he discovered it by accident. It wasn't like he was thoroughly like, he wasn't even testing the XZ Utils or SSHD. He was testing something completely different, and just out of happenstance kind of noticed something was up. So, like, if he could, I don't know. It's kind of a hard situation, and there's definitely going to have to be some, I don't know if soul searching is the right word, but there's definitely going to be some kind of discussions about what this means for kind of open source as a whole, because this definitely was a wake-up call, because there have definitely been supply chain attacks in the past, but nothing, at least to my knowledge, this severe and this, widespread. But again, shout out to Andres for finding this as early as he did, and kind of limiting the damage of the distros that are affected. And yeah, so if you hadn't heard about the XZ Utils backdoor, now you do. If you had already heard about the XZ Utils backdoor, hopefully you got something else out of this, because I know in doing my research for this episode, I kind of picked up, like, I watched a bunch of various different YouTube videos, read various articles, and pretty much every time I did that, I always picked up like another little nugget that I didn't get from one of the other sources. So hopefully, if you had already heard about it, you picked up something new here, or hopefully you just got a better understanding of how this works, and kind of how the backdoor actually works, how it was implemented into the open source supply chain, and I guess at the bare minimum, you figured out if you were vulnerable or not, and how to check for that. So again, I guess before we go, just as a quick recap, to determine if your version of SSH is vulnerable, first off, if you're using the Linux distro you're using does not use systemd, you're fine. But the way that you can check for sure is type LDD/USR/SBIN/SSHD, and if you do not see libLZMA at all, you're good. If you do see libLZMA, next to libLZMA, there will be a path directly to the library itself. If you copy that path and then type ls-l with that path, hit enter, you'll see the full version number. And as long as that version number is not 5.6.0 or 5.6.1, you are fine. So that is, how you can check to see if you in fact have a vulnerable version of XZ Utils and have this vulnerability. So, hope you enjoyed the episode, but we are not quite done, because we have to get back to our trivia question. So this week's trivia question, in the spirit of cybersecurity, is: the onion router, or Tor, was invented in the 1990s. Who invented it? If you said the U.S. Naval Research Lab, congratulations, you got this week's trivia question correct. And I guess one thing that is slightly ironic about that is, governments around the world generally are kind of annoyed at cyber criminals that use the dark web or Tor for their nefarious and illegal activities, yet the government was also the ones that created the dark net and Tor, of course, for a completely different use case, but a little bit ironic nonetheless. But that was your trivia question for the week. Hopefully you got it right. And if you enjoyed this episode, leave a rating and review, and definitely share this episode around, because I think a lot of people need to know, if they haven't already, about this potential vulnerability and the impacts it could potentially have, or just to be, up on the know. And if you have any questions about this episode, since I know we kind of went deep into some fairly technical topics, you can shoot me an email at contact@darkassassinsinc.com. Or if you have any questions or topics for future episodes, you can also send me an email there as well. The link is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.